Electromagnetic clutch. Electromagnetic clutch consists of a fixed electromagnet, which includes magnetic core and the coil, and a movable part which is rotor. There is a non-magnetic insert between the steel rotor and the magnetic core to prevent sticking. The coil is energized with a direct current, which is 750 ampere turns, and our task is to determine the dependence of the attraction force acting on the rotor as a function of the distance between the rotor and the electromagnet. It is not clear from this picture, but the rotor has the disc shape, and what we see is the cross-section of the cylindrical coil and the cylindrical magnetic core. So this model features rotational symmetry, and the blue dotted line is the axis of the rotation. And this can be simulated in two-dimensional axisymmetric model. Okay, let's start QuickField now. In QuickField I create new problem. Problem name clutch. Next. Problem type is magnetostatics. Model class is axisymmetric and length units are millimeters. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD DXF file. Here is the file. Open. Here is the geometry imported. You can see the cross-section of the clutch solenoid. In axisymmetric problems, an axis of rotation is a horizontal one, and we should draw only the upper half of the cross-section. So I will switch to the insert mode and draw the line along the axis of the rotation. Then I switch to select objects mode, select everything below the axis with the rubber band, and delete it. Edit, delete selection. Yes. Now let's zoom to fit. Here you can recognize the rotor, the coil, and the magnetic core and the non-magnetic insert. Let's assign labels. Through labels we will specify material properties. Switch to select objects mode, click the object to select, and type in the label here. This is rotor. Okay. This is coil. This one and this one are the core. Hold the Ctrl button pressed to select multiple objects at the same time. Core. And this is the non-magnetic insert. Okay. In fact, the magnetic field is distributed not only inside the steel parts, but also in the air outside. QuickField cannot simulate infinitely large space, so we need to restrict the simulation domain. Again, switch to insert mode, change the line type to be the half arc, and draw the air block boundary. Okay, switch to select objects mode, click to select. This is the air. Now let's specify physical properties for these labels. Double click the label name in the tree, and for the air I type in the relative magnetic permeability, which is 1. Okay. For the non-magnetic insert, the relative magnetic permeability is 1. For the steel parts, which are rotor and the core, the magnetic permeability is 2000. For the core, 2000 for the rotor. And for the coil I specify relative magnetic permeability, which is 1 for copper and the total current, which is 750 total ampere turns. Okay. That's all for the blocks, but we should also assign labels and physical properties to the boundaries. QuickField automatically assigns proper boundary condition on the axis of the rotation, and I will leave default boundary condition at the external boundary. So the geometry model and the data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button and the mesh will be constructed. Save all problem files and run the analysis. The problem has been solved. Let's take a look at the results. Here you can see the magnetic field lines. You can adjust the field picture and switch on, for example, the color map of the flux density. The correspondence between the colors and the values you can see in the legend. And to get exact value of the field parameters, you can use the local values tool. Just click any point and you will get the flux density value and other parameters. You can edit the point coordinates here. You can also draw an arbitrary contour and get the field distribution along this contour. For example, here I will just click these edges and get the field distribution on the XY plot. And the numbers you can see in the table. Coordinates, flux density, field intensity, and other parameters. You can also use contours to calculate integrals. Contour clear and click to select the rotor. Now follow to the integrals, mechanical force. The force acting on the rotor points to the left. The rotor is attracted to the electromagnet. So we have come to the next task. Calculation of the mechanical force as a function of the rotor position. That is easy, I just need to change the geometry model. Click the rotor to select, move selection by ½ millimeter to the right, build the finite element mesh, save all problem files, solve the problem, and use the contour to calculate the force acting on the rotor. This time it is 103 newtons and before it was 360 newtons. Okay, there is a way to automate force calculation. QuickField has the tool label mover for parametric analysis. The workflow is simple. Choose the base problem, which is clutch.ppm. Add the values to measure. I would like to measure the force acting on the rotor, only the X component. Add. Close. Then specify the steps. Record steps. I would like to move the rotor by 0.5 millimeters to the right. Add the step. Close. And I would like to repeat this step 5 times. Okay. Now I need only to press Get Results button. And here you can see what happens. A set of problems is generated. In each problem the rotor is moved. The problems are simulated and the force is calculated. And the results are stored here in the table. Everything is done and Here is the dependency. Force as a function of the rotor position. For each calculated results, you can open the problem, you can see the field distribution, and you can calculate the force manually. The same value we see in the label mover. The simulation files for these intermediate results are stored in a separate folder, and don't forget to save the label mover file. If you search for the electromagnetic clutch on our website, you will find the example page. Here you can read about problem setup, browse the solution section, and take a look at the resulting pictures. And you can download the simulation files here. Simulation files can be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.